Welcome to the extraordinary and remarkable world of modern aircraft manufacturing. Here, in massive specialized industrial facilities that span hundreds of thousands of square meters, facilities so large that a person walking from one end to the other would take many minutes, some of the most sophisticated and complex machines ever created by human civilization are constructed with meticulous precision and engineering excellence. Modern commercial aircraft represent the absolute pinnacle of mechanical engineering, advanced materials science, and manufacturing excellence, combining thousands upon thousands of complex systems, components, and subsystems into a single integrated flying machine designed to carry hundreds of passengers safely and reliably. Today, we will take you on a comprehensive and deeply detailed journey through the complete process of manufacturing a modern commercial aircraft, from the very initial design and planning phases where aeronautical engineers dream of flight and overcome the challenges of physics, through the fabrication of countless individual components made from advanced materials like aluminum alloys, composite materials, and titanium, continuing through the extraordinarily meticulous assembly process where thousands of parts are joined together with precision riveting and bolting, proceeding through the installation of extraordinarily complex systems including advanced hydraulic systems, sophisticated avionics and flight management systems, extensive electrical systems and mechanical systems, and culminating in rigorous and comprehensive testing that verifies every system functions perfectly and safely, and finally the historic first flight of the completed aircraft as it takes to the sky for the very first time. Watch as massive composite components are fabricated using cutting-edge manufacturing processes that were invented just decades ago. Observe the assembly of thousands of parts as fuselage sections are joined together piece by piece to form the aircraft body. Witness the installation of engines, powerful machines capable of moving an aircraft carrying hundreds of people at speeds approaching the speed of sound. Experience the testing phase where every system is verified with extreme rigor to function perfectly and safely. Witness the moment when the completed aircraft takes flight for the first time, rising into the sky on its own power. This is aircraft manufacturing at the highest level of engineering achievement and industrial capability. This is the story of human ingenuity applied to overcome the fundamental challenge of flight itself. This is manufacturing on a scale and with precision that defines modern industrial capability and represents decades of accumulated engineering knowledge. Before a single piece of aluminum is ever cut, before any manufacturing equipment is activated, before any workers arrive at the factory, the aircraft must be designed with extraordinary precision using advanced computer-aided design software and engineering simulation tools. The design phase for a modern aircraft takes years, sometimes 5, 10, or even more years, and involves hundreds of engineers working in specialized disciplines, each contributing their expertise to the overall design. Aircraft designers and aeronautical engineers use sophisticated computational fluid dynamics software, CFD software, to analyze in meticulous detail how air flows around the aircraft under various conditions. The shape of the fuselage, the main body, the design of the wings, the configuration of the tail surfaces, the engine placement, all are optimized simultaneously to minimize aerodynamic drag while providing sufficient lift to keep the aircraft airborne at various altitudes and speeds. The design must balance competing and sometimes contradictory requirements: fuel efficiency for economy, range for intercontinental travel, passenger capacity for profitability, safety for passenger protection, manufacturing feasibility to keep costs reasonable, and durability for decades of operational service. Watch as engineers manipulate three-dimensional CAD models on computer workstations with multiple high-resolution displays. The model shows every detail with remarkable clarity: the fuselage shape with its precise curves, wing configuration with winglets and control surfaces, engine mounting locations, landing gear position, and thousands of other components. Engineers examine the model from every possible angle, rotating it, zooming in on specific areas, identifying potential problems or interference where components might clash or not fit together. The software automatically checks for these interferences. If a hydraulic line might touch an electrical cable, the software alerts the engineer. Structural engineers calculate with extreme precision the loads the aircraft will experience during every phase of operation: the weight of the structure itself and all contents during normal flight, the aerodynamic forces pushing on the fuselage and wings, the inertial forces when the aircraft accelerates, decelerates, or banks into turns, the impact loads during landing when the aircraft touches down at many meters per second, the cabin pressure differential when the fuselage is pressurized. The structure must support all these loads without permanent deformation or failure. Finite element analysis breaks the entire structure into millions of small elements and calculates stress in each element. Engineers refine the structure repeatedly, adding material where stresses are high, removing material where stresses are low, searching for the optimal balance between strength and weight. Watch as engineers modify the wing structure on the computer. They add reinforcing stringers, small stiffening elements that prevent buckling under compression loads. They calculate the stress in each stringer. They modify the thickness of the skin in different areas based on stress levels. The optimization continues iteratively, computer analysis guiding each decision. The goal is a structure that is strong enough to never fail, even under extreme loads, while being as light as possible to minimize fuel consumption. Thermodynamic engineers design the engines and thermal management systems with extreme care. The engines must produce sufficient thrust to accelerate the aircraft from rest to flying speed on a runway, must maintain speed against aerodynamic drag while carrying full payload, and must provide capability for emergency power. The engines must be efficient to minimize fuel consumption. Fuel represents one of the largest operating costs. Cooling systems must remove excess heat generated by the engines and other systems. Pressurization systems must maintain breathable air in the cabin as the aircraft flies at high altitude where outside air is too thin to breathe. Passengers would lose consciousness if exposed to outside air at cruising altitude. Electrical engineers design the electrical power system with careful redundancy and backup capability. Generators in the engines produce electrical power that is distributed throughout the aircraft using large cables and sophisticated distribution systems. Backup systems using batteries ensure critical systems continue operating if main power is lost. The electrical system must power countless systems. Flight control computers that make thousands of calculations per second, cabin lighting for passenger visibility and comfort, navigation systems that determine the aircraft's position with accuracy of meters, communication systems connecting the aircraft to the world, entertainment systems for passenger comfort, and many others. Avionics engineers design the flight control systems and navigation systems with extraordinary sophistication. Modern aircraft use fly-by-wire systems where pilot inputs, movements of the control columns and pedals, are transmitted to computers rather than using mechanical linkages. The computers automatically adjust control surfaces to maintain stable flight and to respond appropriately to pilot inputs. Navigation systems use GPS satellites for position determination, inertial measurement units that measure acceleration, and ground-based navigation aids. The computers automatically integrate all this information to determine the aircraft's position and guidance. Software engineers develop the control system software that might contain millions of lines of code. Every possible scenario is considered: normal operation, engine failure, system failures, extreme weather, bird strikes. The software is tested exhaustively in simulation before ever being installed in a real aircraft. The design process produces detailed drawings showing exactly how the aircraft will be manufactured. These drawings specify materials for each component, which aluminum alloy, which composite, which fastener type. Dimensions are specified with tolerances. Perhaps a hole must be 10.0 millimeters in diameter, with tolerance of plus 0.05 millimeters or minus 0.05 millimeters. Assembly procedures are specified. Thousands of details are documented. The drawings become the manufacturing blueprint from which production will proceed. The design is validated through multiple means. Computational analysis predicts performance. Wind tunnel testing verifies aerodynamic characteristics. Scale models are built and tested. Full-size mock-ups are constructed and inspected. Only after all validation is complete is the design finalized and authorized for manufacturing. Modern aircraft are constructed using advanced materials carefully selected for their specific properties. Aluminum alloys provide strength combined with light weight. Aluminum weighs 1/3 as much as steel but can be alloyed with other elements to achieve strength comparable to steel. Different aluminum alloys are used in different locations based on their properties. Composite materials, fiber-reinforced plastics with carbon fiber or fiberglass reinforcement, are used for non-structural components and increasingly for primary structure. Composites are lighter than aluminum and resist fatigue, the repeated stress cycling that occurs during flight. Titanium alloys are used where extreme strength and heat resistance are needed, near engine exhausts where temperatures are very high, in engine components where strength must be maintained at high temperature. The fabrication of aircraft components begins at specialized supplier facilities located around the world. Large aluminum sheets arrive at the fabrication facility. These sheets might be several meters long and meters wide, weighing thousands of kilograms. The sheets are cut to precise sizes using numerical control equipment. Fuselage skin sheets are cut from large aluminum blanks using precision cutting equipment. Computer numerical control equipment programmed with exact dimensions cuts the sheets to exact shapes and sizes. The cutting is smooth and precise. The cut edges have minimal irregularities. Holes are drilled in precise locations for fasteners using CNC drilling equipment. The holes must be perfectly aligned. If holes are misaligned even by millimeters, components won't fit together properly during assembly and rework would be required. Composite components are fabricated using specialized processes that are both an art and a science. Carbon fiber or fiberglass fabric is positioned in careful layers. Each layer is in a specific orientation. Perhaps the first layer is oriented horizontally, the next layer at 45 degrees, the next layer vertically, creating a multi-directional reinforced structure strong in all directions. The fabric is saturated with epoxy resin, a polymer that is liquid at room temperature but will solidify into a hard plastic when heated. Watch as composite wing components are laid up in a large specialized mold. Workers carefully position layers of fiber fabric in specific orientations following the design specifications. The orientation of the fibers is critical. If fibers are not aligned correctly, the strength will be insufficient. Each layer is saturated with resin applied by hand with brushes or by spraying. The process is labor-intensive and requires skilled workers who understand the importance of proper positioning. Layer after layer is added, building up the desired thickness and strength. The process continues for hours, with workers carefully positioning each layer. Once all layers are positioned and saturated, the assembly is placed in an autoclave, a large pressure vessel similar to a giant oven. The autoclave is sealed and heat and pressure are applied gradually. Heat accelerates the chemical reaction that causes the resin to cure and solidify. Pressure helps consolidate the layers, removing air pockets and ensuring good fiber resin contact. The process takes many hours. Temperature is carefully controlled. Too high and the resin degrades, too low and curing is incomplete. When the cycle is complete and the part has cooled, it is removed from the autoclave as a hardened component, a strong, rigid structure with excellent strength-to-weight ratio. Forged components are manufactured at specialized forging facilities equipped with massive hydraulic presses. Large aluminum or titanium billets are heated to elevated temperature to make the material plastic and workable. The heated billets are positioned in dies-shaped molds in the hydraulic press. The press applies enormous force, deforming the material to the desired shape. The forging process aligns the metal crystals in the direction of the applied force, creating components with superior strength compared to machine components made by removing material from a larger block. Landing gear components are forgings. They must withstand the impact of landing and the entire aircraft's weight. Forging creates a structure that can safely support these loads. Machined components are produced using computer numerically controlled machine tools. These machines automatically perform sequences of operations: drilling, boring, milling, turning. A CNC program downloaded into the machine tool controls every operation. The machine tool is far more precise and consistent than any human operator could be. Aircraft structural components requiring high precision are manufactured using CNC machines. The machines run continuously, sometimes 24 hours a day, producing components. Watch as a CNC machine tools a structural component. The workpiece is clamped in the machine. The cutting tool rotates at thousands of revolutions per minute. The workpiece advances slowly toward the rotating tool. The tool cuts away excess material, creating the desired shape. Different tools, drills, and mills, boring tools, are automatically changed as the program directs. Coolant liquid cools the tool and workpiece. The machine operates with mechanical precision. The tool position is controlled to within fractions of a millimeter. The machining continues for minutes or hours, gradually transforming the raw material into a finished component. Sheet metal components are manufactured using punching and bending operations. Large aluminum sheets are positioned in dies mounted in massive mechanical presses. The press applies force and the dies shape the metal into the required form. Skin panels for the fuselage are manufactured this way, large quantities of identical panels, each one precisely shaped to fit into the aircraft structure. Fasteners, rivets, bolts, and fastening systems are manufactured to exacting specifications in large quantities. Rivets must provide secure permanent joints that will not loosen during flight. The rivet material must not corrode where aluminum and steel are in contact. Bolts must have precise thread specifications so they fit properly into threaded holes. Lock washers prevent vibration from loosening fasteners during flight. Each fastener is manufactured to specifications and inspected for quality. All components are rigorously inspected before being shipped to the final assembly facility. Dimensional inspection using precision measuring instruments, calipers, micrometers, coordinate measuring machines, verifies that components have the correct size and shape within specified tolerances. Material inspection verifies that the material is the correct type, aluminum alloy 7075 instead of 6061 for example, which would have different strength properties. Quality control testing includes tensile testing, pulling samples of material until they break to verify they meet minimum strength requirements. Corrosion testing immerses components in salt spray to verify they resist corrosion. The testing is rigorous because component failure during flight could be catastrophic. Completed components are organized, labeled, and packed carefully for transportation to the final assembly facility. Some components travel thousands of kilometers from supplier facilities to the main assembly plant. The fuselage, the main body of the aircraft, is assembled from multiple large sections fabricated at different facilities or different locations within the same facility. The fuselage sections are eventually transported to the final assembly facility where they are joined together to form the complete aircraft body. The sections might include the forward fuselage containing the cockpit, the forward cabin fuselage, the main deck cargo section, the rear fuselage, and the tail cone. The manufacturing facility is enormous. A massive building that might span 300 meters in length, 100 meters in width, and 50 meters in height. Inside, fuselage sections are positioned on special assembly jigs, steel frames designed to hold the fuselage sections in precise alignment during assembly. The jigs are computer controlled and can adjust to minute tolerances. The first section, perhaps the forward fuselage containing the cockpit and forward cabin, is carefully positioned on the assembly jig. The section rests on special supports that hold it level and aligned. Hundreds of alignment holes are pre-drilled in the mating surfaces. These holes are where fasteners will pass through to join sections together. The holes must be perfectly aligned for the sections to fit together. Watch as the next fuselage section is maneuvered into position adjacent to the first section. The sections must align perfectly. The holes must line up so fasteners can pass through both sections, and the mating surfaces must fit together without gaps or misalignment. The positioning is done with extreme care, using precision positioning equipment and laser alignment systems to verify perfect positioning. The jig can adjust in small increments, millimeters or even smaller, to achieve perfect alignment. Workers monitor alignment displays showing the current position and the target position. Adjustments are made until the sections are positioned perfectly. Once sections are positioned with perfect alignment, fastening begins. Thousands of fasteners must be installed to join the sections together and create a strong, rigid structure. The number of fasteners is enormous, perhaps 10,000 or more fasteners to join two fuselage sections. 4 riveted construction, pneumatic rivet tools, powered by compressed air, drive rivets through aligned holes, permanently joining the sections together. The riveting is performed by skilled technicians, riveters, who have specialized knowledge of proper rivet installation. Different rivet types are used in different locations. Solid rivets in most locations, blind rivets in locations where access is limited. Watch the riveting process in detail. A riveter positions a pneumatic rivet gun over a hole containing a rivet. The rivet is a cylindrical piece of metal with a head on one end. The rivet is inserted through aligned holes in the two sections being joined. The riveter positions the rivet gun with the bucking tool, a tool that supports the backside of the rivet, positioned behind the rivet. The gun is activated, driving the rivet and deforming the end, creating a permanent joint that locks the two sections together. The process is repeated thousands of times. The sound of rivet guns echoing through the assembly facility is deafening, a constant staccato of impacts. Rows of rivets create visible lines along the fuselage, showing the assembly progress. 4-bolted construction. Large bolts are inserted through aligned holes and tightened with controlled torque to achieve proper tension without damaging components. The bolts must be tight enough to transfer loads but not so tight that they crack or strip the threads. As fuselage sections are joined, additional sections are added: mid-fuselage sections, rear fuselage sections, each joined to the previous section with meticulous care. The fuselage grows longer as sections are fastened together. Thousands upon thousands of fasteners are installed. Quality inspectors verify that fasteners are properly installed and aligned. Inspectors use special tools to verify rivet quality, checking that the rivet head is properly formed and the rivet is fully seated. The wings are attached to the fuselage. This is a critical operation because the wing attachment points must be able to support the wing lift forces during flight and landing. The wing lift forces are enormous, perhaps the entire weight of the aircraft or more. Large pins or bolts, sometimes multiple centimeters in diameter and made of high-strength steel, attach the wings to the fuselage structure. The attachment must be extremely strong because the wing loading is enormous and failure would be catastrophic. Watch as wings are positioned and attached to the fuselage. The wing is carefully lowered onto the fuselage using cranes and precision positioning equipment. Alignment pins position the wing correctly. The pins slide into matching holes and guide the wing into the correct position. Workers install the large bolts that will permanently attach the wing. Multiple bolts, perhaps 20 or more, pass through aligned holes in the wing attachment brackets and the fuselage structure. Workers thread nuts onto the bolts and tighten them with hydraulic torque wrenches. Each bolt is tightened to the exact specification determined by engineers. The force applied is measured to ensure the correct tension. The bolt must be tight enough to safely support the load but not so tight that it deforms components or separates the joint during flight. The tail section is attached to the rear fuselage. The tail components, the horizontal stabilizer and vertical fin, are fastened to the fuselage structure using many bolts. Like the wing attachment, the tail attachment must be strong because these surfaces carry significant aerodynamic loads during flight. Landing gear is attached to the fuselage at the landing gear attachment points. The landing gear must support the aircraft weight during takeoff and landing. The attachment points are among the strongest parts of the fuselage structure. The landing gear extends from the fuselage and retracts into the fuselage during flight to reduce drag and weight. The control surfaces, ailerons on the wings, elevators on the horizontal tail, rudder on the vertical tail, are attached and tested for smooth operation. These surfaces control the aircraft's orientation in flight. They must move freely and respond quickly to control inputs from the pilots. Once the basic structure is complete and the airframe is substantially assembled, the aircraft's operational systems must be installed. The hydraulic system provides power to move control surfaces, extend and retract landing gear, operate wheel brakes, and operate other mechanical systems. Modern aircraft have multiple independent hydraulic systems, typically 3 or more, providing redundancy so if one system fails, others continue operating and the aircraft remains controllable. Large hydraulic pumps are mounted in the engines or in the fuselage structure. The pumps are driven by the engines and produce pressurized hydraulic fluid at pressures of perhaps 3,000 pounds per square inch, extremely high pressure. The fluid is distributed through rigid aluminum tubing and flexible hoses throughout the aircraft. The fluid is routed to actuators, devices that convert hydraulic pressure and flow into mechanical motion. Watch as hydraulic components are installed throughout the aircraft interior. Rigid aluminum tubing is carefully routed through the fuselage, supported at intervals by brackets clamped to the structure. The tubing must be protected from mechanical damage. If the tubing is dented or punctured, the hydraulic system will leak and lose pressure. The tubing is positioned away from hot surfaces and electrical systems. The routing follows the design specifications exactly. The designer has determined the optimal path that minimizes tubing length while avoiding other systems. The tubing is connected using specialized fittings, connections that are swaged or flared to create leak-proof joints. The fittings must be perfectly sealed because even small leaks would result in gradual pressure loss. Flexible hoses connect moving components to the rigid tubing. The hoses are reinforced with multiple layers of steel wire to withstand the high pressure. The connections are sealed with O-rings, rubber seals that prevent leakage while allowing relative motion between components. Junction blocks are installed at strategic locations where the hydraulic fluid is distributed to different systems. These blocks contain passages that allow the single stream of high-pressure hydraulic fluid from the pump to be split into multiple streams, each directed to a different system. Pressure relief valves protect the system from overpressure by opening and allowing fluid to return to the reservoir if pressure exceeds safe limits. Fuel system components are installed with extreme care because the fuel system is safety critical. Large fuel tanks are integrated into the wings and fuselage. The wings contain the majority of fuel. Fuel pumps move fuel from tanks to engines. Fuel filters remove contaminants. Any particles of debris or water would damage the engine. Fuel quantity indicators show pilots how much fuel remains. The fuel system must be designed so fuel cannot leak. Even a small leak would result in unacceptable fuel loss during flight. Watch as fuel tanks are sealed and pressure tested. The tanks are filled with water, then pressurized with air to perhaps 50 pounds per square inch. The system is monitored for any pressure drop that would indicate a leak. If any leaks are found, they must be repaired before the system is accepted. Once confirmed leak-free, the water is drained and the system is ready for fuel. The testing is absolutely critical. Fuel leaks are unacceptable for safety reasons. Air conditioning and pressurization systems are installed with careful attention to ensuring they function reliably. Hot air is extracted from the engine, air that has been compressed and heated by the engine compressor. This hot air is too hot for the cabin, so it is cooled before being supplied to the cabin. Cooling is achieved by mixing the hot engine air with cold outside air at high altitude, or by passing the air through heat exchangers that transfer heat to outside air. The system maintains comfortable temperature in the cabin, typically around 20 degrees Celsius during flight at any altitude. Watch as air ducting is routed throughout the aircraft. Large ducts carry hot air from the engines. Smaller ducts distribute conditioned air to different cabin zones. Valves controlled by the environmental control system regulate the flow of air and control the temperature. Temperature sensors throughout the cabin send signals to control systems. The control systems adjust the mix of hot engine air and cold outside air to maintain the desired cabin temperature. The system is complex but essential for passenger comfort and safety. Pneumatic systems use compressed air for various purposes. Air brake systems use compressed air to apply brakes. Equipment starting systems use compressed air to start the engines. De-icing systems use heated compressed air to prevent ice accumulation on wings and engine inlets. The compressed air comes from the engines where air is compressed as part of the engine operation. Fire detection and suppression systems are installed to prevent fires and manage them if they occur. Heat sensors detect fires in engine compartments. Fire suppression systems in engine compartments discharge fire-suppressant chemicals if fire is detected. Smoke detection systems alert the crew to fire dangers in cargo compartments and lavatories. The systems are interconnected. If fire is detected in one location, alarms sound and the crew is alerted. The electrical system provides power to operate the aircraft during flight. Engine-driven generators mounted on each engine produce electrical power. When engines are off or if generator output is insufficient, batteries provide backup power. The electrical power is distributed to every space in the aircraft. Thousands of electrical loads must be powered. Main electrical cables are routed throughout the aircraft from the generators to distribution panels. The cables must be large enough in cross-sectional area to carry the required current without excessive voltage drop. Voltage drop, the reduction in voltage that occurs as current flows through cables, must be minimized because excessive voltage drop reduces equipment performance. The cables are protected by conduits and cable trays and routed away from heat sources that could damage insulation. Watch as electrical technicians route massive power cables through the fuselage. The cables are organized in large cable trays and secured at regular intervals. Cable markers identify where each cable goes and what it powers. Color coding helps technicians identify cable function and voltage level. Red for DC power, green for AC power, for example. The routing is complex because cables must avoid hydraulic lines, fuel lines, and structural elements. The routing must allow future maintenance and replacement of cables. Electrical distribution panels are installed in the cockpit and throughout the aircraft. These panels contain circuit breakers that protect circuits from overload. If a circuit draws too much current, the circuit breaker automatically opens, disconnecting power and preventing damage. Switches allow pilots and crew to control aircraft systems, switching engines on or off, switching electrical systems on or off. Light indicators show system status. Green lights indicating normal operation, amber lights indicating caution, red lights indicating failure. Flight control computers and avionics equipment are installed with extreme care. These computers process pilot inputs, manage engine operation, navigate the aircraft, and control countless systems. Modern aircraft have multiple redundant computers. If one fails, others continue operating. The equipment is very expensive and sensitive to vibration and electromagnetic interference. Installation must be done carefully to isolate the equipment from vibration and to shield it from electromagnetic interference. Watch as avionics technicians install complex electronic equipment. Navigation systems receive GPS signals and signals from ground-based navigation systems. Flight management systems calculate optimal flight paths and control aircraft navigation and speed. Weather radar systems detect precipitation. Terrain awareness systems warn pilots of terrain ahead. Collision avoidance systems detect other aircraft and warn of potential collisions. Each system is carefully installed and tested. The equipment must function reliably because pilot dependence on these systems is absolute. Lighting systems are installed throughout the aircraft. Navigation lights on the wings and tail allow other aircraft to see the aircraft at night. Red light on the left wing, green light on the right wing, white light on the tail. Landing lights mounted on the landing gear or fuselage illuminate the runway during approach and landing, making the runway visible to pilots. Cabin lights illuminate the interior for passenger visibility and comfort. Overhead lights for general illumination. Reading lights for passenger comfort, floor-level lights for emergency egress. Cockpit lights allow pilots to see their instruments and controls. Emergency lighting illuminates exit routes if main power fails. Communication and navigation antennas are mounted on the fuselage exterior. Radio antennas transmit and receive communication signals. Pilots can communicate with air traffic control, other aircraft, and ground facilities. Navigation antennas receive GPS signals and signals from ground-based navigation systems. The antenna positions are critical for proper signal reception. Antennas must not be shaded by fuselage structure or other antennas. Once major systems are installed, the aircraft interior is configured. Seats are installed in precise rows, aligned with remarkable precision. Each seat is securely fastened to the seat rails with multiple bolts. Seat belts with sophisticated locking mechanisms are installed. The belts must hold passengers securely but must also release instantly in emergency situations. Overhead compartments provide passenger luggage storage. The overhead compartments are integrated into the fuselage structure, utilizing the space between the fuselage skin and the cargo hold structure above. Watch as seat rows are positioned. Workers carefully align seats in rows using alignment fixtures. The spacing between rows is carefully calculated to provide adequate passenger space, typically 31 to 32 inches, and emergency egress paths. Seats must be comfortable but durable for years of use. The seat cushions are firm to provide adequate support and maintain their shape through years of use. Seat covers are fire-resistant material that will not burn or produce toxic gases. Cockpit equipment is installed and configured with extreme precision. Pilot seats mounted on adjustment rails allow pilots to adjust their position for comfort. Control columns, the yokes that pilots manipulate to control the aircraft, are installed. Throttle levers, landing gear control levers, and countless switches and displays are positioned. The layout must be ergonomic. Pilots must be able to reach and see all controls easily. Redundant systems provide backups if primary systems fail. The instrument panel displays show flight parameters, altitude, speed, heading, engine power, fuel quantity, and many others. Lavatories are installed and plumbed. The lavatory system must handle human waste in flight. A vacuum system creates suction to move waste from toilets to a holding tank. The vacuum system is the same technology used in aircraft lavatories for decades. The system is self-contained. No waste can leak into the aircraft structure. Holding tanks contain the waste until the aircraft lands and the tanks are emptied by ground equipment. Galleys are installed where flight attendants prepare beverages and meals during flight. Water systems provide fresh water for beverages. Electrical outlets power equipment. Storage compartments hold supplies. The galleys must be organized for efficient operation and minimal space usage. Emergency equipment is installed throughout the aircraft. Life vests are stowed under seats, accessible to passengers. Oxygen masks drop from overhead compartments if the cabin loses pressurization. Evacuation slides attached to doors inflate if deployed, allowing passengers to slide from the aircraft to the ground during emergency evacuation. First aid kits and emergency equipment are positioned in accessible locations. Every passenger must be able to reach emergency equipment quickly if needed. Insulation and sound dampening materials are installed. Fiberglass insulation maintains cabin temperature, reducing heat loss during cold weather and reducing solar heating during hot weather. Sound dampening materials reduce engine noise inside the cabin, creating a more comfortable environment for passengers. Vapor barriers prevent moisture from accumulating inside the structure, which would lead to corrosion and mold growth. Interior cabin walls, flooring, and ceiling panels are installed. The interior materials must be fire-resistant to provide safety in case of fire. The materials must not burn or produce toxic gases. The interior is designed to be attractive while remaining functional and durable. The materials must withstand years of wear from thousands of passengers using the aircraft. Watch as interior panels are fastened in place. Workers carefully position panels and secure them with fasteners. The panel joints are aligned to provide a finished, professional appearance. The interior gradually transforms from a bare structure with exposed systems into a completed cabin environment where passengers will spend hours during flight. Emergency exits are clearly marked and lights illuminate the exit paths. The exits must be easily accessible and clearly visible so passengers can quickly evacuate if needed. Exit doors are tested to ensure they can be opened quickly by passengers without special training. The aircraft engines, massive machines capable of producing tens of thousands of kilograms of thrust, are installed late in the assembly process. The engines are assembled at specialized engine manufacturers like Rolls-Royce, General Electric, or Pratt & Whitney in separate facilities. The assembled engines are tested at the engine manufacturer before being shipped to the aircraft manufacturer. The engines are then installed on the aircraft. The engines are enormous and extraordinarily expensive. Each engine for a large aircraft might cost $20 to $50 million or more. The engines represent advanced technology developed over decades. Each engine contains thousands of components designed to operate at extreme temperatures and pressures. The turbine blades operate at temperatures exceeding 1000 degrees Celsius while spinning at tens of thousands of revolutions per minute. Watch as an engine is carefully transported to the aircraft. The engine is mounted on a special cradle designed to support its weight and protect it during transport. The cradle is positioned on a large truck. The engine is carefully maneuvered into the manufacturing facility and positioned under the aircraft wing. The engine is enormous, taller than a person and wider than a car. Multiple cranes and positioning equipment carefully position the engine under its mounting point on the wing structure. Workers attach the engine to the mounting points on the wing structure. Multiple large bolts and pins secure the engine. The bolts must be tightened with controlled force to achieve proper tension. The positioning must be precise. The engine must be perfectly aligned so that the engine centerline aligns with the aircraft's center of gravity and thrust vector. Any misalignment would cause undesirable yaw during powered flight. The aircraft would pull to one side. Alignment is verified using precision instruments and laser alignment systems. Technicians measure the distance from the engine to reference points on the aircraft structure. The measurements are compared to target values determined during aircraft design. If the engine is misaligned, adjustments are made. The process continues until the engine is perfectly positioned. Once the engine is mounted and aligned, connections are made. Fuel lines connect the aircraft fuel system to the engine fuel controls. The fuel must reach the engine at the correct pressure and flow rate. Hydraulic lines connect aircraft hydraulic systems to engine-driven accessory equipment. Electrical connections power engine controls and monitoring systems. Air intake ducts connect the engine to external air. The engine requires tremendous quantities of air during operation. Exhaust systems route hot gases away from the aircraft structure to prevent damage. Watch as technicians make final engine connections. Each connection is verified to ensure it is secure and will not leak. Engine control linkages are connected and adjusted. Engine monitoring systems are installed and calibrated. Engine starts are tested to ensure the engines respond to control inputs as expected. Landing gear is installed. Wheels, tires, shock absorbers, brakes and control mechanisms. The landing gear must support the aircraft weight during takeoff and landing. The gear must extend smoothly during descent and retract smoothly during climb. The shock absorbers must absorb the impact of landing without allowing excessive deflection. The wheels must be the correct size and properly balanced for smooth operation without vibration. The landing gear attaches to the fuselage with large bolts and pins at attachment points designed to be among the strongest parts of the fuselage structure. The attachment points must be extremely strong because the landing gear experiences very high loads during landing. A landing might involve multiple gs of vertical acceleration as the shock absorbers compress. The attachment must safely handle these loads. Watch as landing gear is positioned and installed. The complex assembly is carefully aligned and fastened. Every component is checked to ensure proper function. The gear is tested, extended and retracted to verify smooth operation. The brakes are tested. The wheels are spun and verified to rotate freely without excessive vibration. All major systems installed, the exterior is prepared for painting. The aircraft is thoroughly cleaned to remove any contaminants, dust, oils or manufacturing residue. Any surface defects are repaired. The exterior is sanded smooth in areas as needed using fine grit sandpaper, creating a smooth surface for paint adhesion. Primer is applied to protect the aluminum from corrosion. The primer provides a base layer that promotes paint adhesion to the aluminum and provides corrosion protection. The aircraft is moved through a large paint booth where spray equipment applies primer evenly. The primers are typically zinc chromate or other epoxy-based materials. Multiple thin coats are applied rather than one thick coat to ensure even coverage and proper adhesion. The final paint scheme is then applied. Airlines typically apply distinctive livery, company colors and logos, to the aircraft. The aircraft fuselage might be white with a colored stripe or design. The tail section typically features the airline's distinctive logo. The aircraft belly might be a different color. The paint is carefully applied to create an attractive appearance while providing protection from ultraviolet radiation and environmental degradation. Watch as paint is sprayed on the aircraft. The spray equipment creates a fine mist of paint that adheres to the surface. The painters must work methodically to ensure even coverage. Too much paint in one area causes drips and sags, too little leaves bare spots. The paint must be allowed to cure between coats. Curing times vary depending on the paint type and environmental conditions. Some paints cure at room temperature, others require heating. Multiple coats of paint are applied, typically a primer coat, a base color coat and a clear protective coat. The clear coat provides additional protection and enhances the appearance. The final finish should be smooth and glossy, showing no drips or sags. Poor painting work is immediately visible and creates a poor first impression. Decals and graphics are applied showing the aircraft registration, the unique identifier painted on the tail. The registration might be N12345 for U.S. aircraft. The manufacturer name and aircraft model designation are displayed, perhaps Boeing 787 or Airbus A350. Airline logos and branding are applied to the fuselage. Safety markings indicate emergency exits and equipment locations. The windshields and windows are installed. Cockpit windshields must be extremely strong to withstand bird strikes and pressure differences between inside and outside the aircraft. The windshields are typically laminated glass or acrylic multiple centimeters thick. Cabin windows are smaller but must also be strong. The windows are sealed with gaskets to prevent air leakage. The windows are tested to ensure they do not leak and can withstand the pressure differences that occur during flight. Interior lighting is tested and adjusted. All exterior lights are tested to ensure they function properly. Navigation lights must be visible from required distances. Landing lights must illuminate the runway adequately. Anti-collision lights must be visible at night. The intensity and color of each light is verified. Before the aircraft flies, comprehensive testing is performed to verify that all systems function properly and safely. Testing takes weeks or months and involves hundreds of technicians working in coordinated teams. The airframe is inspected thoroughly using non-destructive testing methods that reveal defects without damaging the aircraft. X-ray testing reveals internal defects in welds or riveted joints. Ultrasonic testing uses sound waves to detect cracks or delaminations in composite materials. Eddy current testing detects surface and near-surface defects. The testing is systematic. Every critical area is inspected. Hydraulic systems are pressure tested. The systems are filled with hydraulic fluid, pressurized to operating pressure, and monitored for leaks. Any leaks are identified and corrected. Flow rates are measured to verify the pumps deliver the required flow. Control valve responses are tested to verify the valves function properly. Actuators are operated through their full range to verify they move smoothly. Fuel systems are tested. Fuel is pumped through the system at operating flow rates. Flow rates are measured and verified to match design specifications. Fuel filters are verified to remove contaminants. Fuel quantity indicating systems are tested to verify they accurately display the fuel quantity. Fuel crossfeed systems are tested to verify fuel can be transferred between tanks as needed. Electrical systems are tested. Generators are operated and output voltage is verified to remain within acceptable range. All circuits are tested under load. Backup battery systems are tested to verify they provide power if main generators fail. Emergency power systems are tested. Environmental control systems are tested. Temperature is regulated to verify the cabin can be maintained at comfortable temperatures. Humidity is controlled. Pressurization is verified. The cabin pressure is maintained at levels equivalent to an altitude of perhaps 2,000 meters even when the aircraft flies at 10,000 meters altitude or higher. The rate at which cabin pressure changes must be controlled to prevent passenger discomfort. Avionics systems are tested extensively. Navigation systems are verified using GPS test signals. Communication systems are tested with radio transmission equipment. Flight management systems are tested with simulated flight data. Control systems are verified to respond appropriately to test inputs. Fire suppression systems are tested. Fire detection sensors are verified to alarm correctly. Fire suppression discharge systems are tested to verify they release suppressant properly. Control surfaces are tested. Control surfaces are moved through their full range. Response to control inputs is verified. The hydraulic actuators must respond quickly and smoothly to control input commands. The aircraft is towed to the runway. Ground support equipment is connected. The aircraft electrical system is verified. All fluid levels, fuel, hydraulic fluid, coolant, are verified to be correct. The engines are started for the first time they will actually run since being installed. The engines are run at increasing power levels, and technicians monitor engine operation for any problems. Engine temperatures, pressures, and vibrations are within normal ranges. Engine performance is logged. After all ground testing is complete and all systems are verified to function properly, the aircraft is ready for its first flight. The historic moment when the aircraft that has taken months or years to construct finally flies is extraordinary and represents the culmination of countless hours of work. The aircraft is towed to the runway by a tug. The flight crew, experienced test pilots with thousands of hours of flight experience, boards the aircraft. These pilots have tested many aircraft and understand the risks and procedures. Ground crew verify all systems one final time. Clearance is received from air traffic control. The runway is cleared of all other aircraft. Watch as the aircraft taxis down the runway. The engines accelerate smoothly, power increasing. The airspeed increases as the aircraft accelerates. As the aircraft approaches flying speed, perhaps 170 kilometers per hour, the test pilot gently pulls back on the control column. The nose rises, the wings generate lift, and the aircraft becomes airborne for the first time. The aircraft rises slowly into the sky on its own power, supported entirely by lift from the wings. The moment is extraordinary. An aircraft that was a collection of parts months earlier is now flying. The aircraft climbs slowly into the sky. Test pilots monitor every system: engine performance, hydraulic pressure, electrical power, control surface response. Telemetry data is transmitted continuously to ground stations where engineers monitor the flight. Every system is verified to function properly. The pilots perform gentle maneuvers, gentle turns, climbs, descents. The handling characteristics are verified. The control response is checked. Nothing is pushed to extremes. The first flight is cautious and conservative. The aircraft is slowly put through its paces, with pilots testing each system methodically. The aircraft performs gentle turns, verifying that the control surfaces function properly and the aircraft handles as expected. The aircraft climbs to a modest altitude, perhaps 3,000 meters, where the air is thinner and the aircraft's ability to climb decreases. At high altitude, the engines are less powerful because they are air-breathing engines and thin air means less oxygen available. The climb performance is verified to match predictions. The aircraft descends back toward the airport. The aircraft approaches the airport for landing. The test pilots request landing clearance. The approach is gentle and methodical. The landing gear is extended and locked, a critical operation. The flaps are extended incrementally to increase lift at lower speed. The aircraft descends toward the runway. The airspeed decreases as the aircraft approaches landing. The pilots begin the descent, carefully controlling the descent rate. The runway appears ahead. The landing lights illuminate the runway. The wheels touch the ground gently. The aircraft has returned from its first flight safely. The moment is celebrated. The aircraft has proven it can fly. Following the first flight, additional certification flights are performed. The aircraft is tested to verify it meets specifications. Extreme conditions are tested. High-altitude performance to verify the aircraft can fly at the altitudes for which it was designed. High-speed performance to verify the aircraft can achieve design cruise speed. Maximum weight testing to verify performance when carrying maximum payload. Cold weather operation testing, hot weather operation testing. All testing must be completed before the aircraft is certified for commercial service. Regulatory authorities must approve the aircraft before it can carry paying passengers. The authorities conduct their own testing and inspections. Only after all testing is complete and all authorities approve is the aircraft certified for commercial operations. Once certification is complete and all tests are passed, the aircraft is ready for delivery to the airline customer. The aircraft receives its final paint job with the airline's colors and livery. The interiors are configured according to the airline specifications. The exact seat type, seat configuration, and special equipment the airline requires. Watch as the completed aircraft is presented to the airline. Executives and employees gather for the delivery ceremony. Photographers and media document the moment. The aircraft represents a major investment. Many hundreds of millions of dollars. The aircraft will operate for decades, carrying hundreds of thousands of passengers and earning revenue for the airline. The aircraft is ferried to the airline's home base. The crew, now airline pilots rather than test pilots, flies the aircraft to its operational base. The aircraft is positioned at the gate where passengers will board. The aircraft enters service. Passengers board through the jet bridge. The aircraft departs, carrying passengers on revenue flights. The aircraft that was assembled piece by piece in the manufacturing facility is now a working transportation system carrying people. The aircraft operates flight after flight, day after day, year after year. Maintenance is performed regularly, oil changes, inspections, part replacements. The aircraft is maintained in safe operational condition. The aircraft structure is regularly inspected to verify no cracks or corrosion is developing. Modern aircraft typically have operational service lives of 20 to 30 years, accumulating hundreds of thousands of flight hours and carrying millions of passengers safely. A modern commercial aircraft represents one of humanity's greatest engineering achievements. The aircraft combines thousands of sophisticated systems into a single integrated machine. The aircraft operates at altitudes where the outside air temperature is -50 degrees Celsius and the air pressure is 1% of sea level pressure. The fuselage maintains pressurized air inside for passenger comfort. The engines produce enormous power while consuming fuel efficiently. The control systems respond instantly to pilot inputs, adjusting the aircraft's attitude and flight path with precision. The design of an aircraft requires knowledge from many engineering disciplines: aerodynamics, structural engineering, thermodynamics, controls, avionics, human factors, materials science, and many others. The synthesis of all this knowledge into a single aircraft design is a remarkable achievement that takes years. The manufacturing of an aircraft requires the coordinated effort of thousands of workers and engineers throughout the world. Component fabrication specialists create individual components. Assembly workers join components together piece by piece. Electricians wire the aircraft with thousands of electrical connections. Mechanical technicians install engines and systems. Avionics specialists install navigation and control systems. Inspectors verify quality throughout the process. Each person contributes their expertise to the project. The aircraft will carry thousands of passengers safely from one place to another over its lifetime. Passengers trust their lives to the aircraft, a trust that is earned through decades of safe operation and continuous improvement. The aircraft is built to exacting safety standards. Every system is redundant. If any single component fails, other systems provide backup capability. Failure of any single component will not compromise safety. The aircraft represents human courage, the courage to dream of flight and the determination to achieve it through engineering and manufacturing excellence. The Wright brothers' first flight lasted only 12 seconds. Today, aircraft fly around the world, carrying hundreds of passengers at nearly the speed of sound, high above the clouds, demonstrating the remarkable achievements of human civilization. Thank you for joining us on this comprehensive journey through aircraft manufacturing. We hope you have gained deep appreciation for the remarkable engineering, meticulous manufacturing, rigorous testing, continuous improvement, and dedicated effort required to bring these magnificent flying machines into being.
gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Exit shift like clouds in the dark. A symphony of cogs finding their spark. Atmosphere fades like a fading dream. The hum recedes into the machine. Warmth dissolves into the still serene. A gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Tessers shift like clouds in the dark. A symphony of cogs finding their spark.